So I'm John Schanck. I am going to be talking about putting post-quantum cryptography into Tor. We've seen a lot of really cool new proposals for systems. I haven't heard a lot of people using post-quantum cryptography. So rather than start out by introducing Tor, which you all know, I'm going to start out trying to motivate why we might think about quantum adversaries today. So here's a little historical context. This is a computer from 1932. It's an interesting computer because it was built by Derek Lehman. It's a factoring machine. And it was the fastest factoring machine until well into the 1960s. This is a quantum mechanical calculator from 2014. It doesn't do much yet, but it does do something interesting. If you look at the title there, superconducting quantum circuits at the surface code threshold for fault tolerance, what they're saying is that if they could build more of these qubits at the same quality that they do right now, then they would actually be able to make arbitrarily large quantum computers, which is a little bit scary. Although the picture's a little misleading because it's just the little part in that innermost box right there. And there's so much classical circuitry, so much microwave electronics outside, that's what's preventing us from building large quantum computers right now. There's a little dotted thing there that's for the other 4 qubits, so that's multiplied a few times. Okay, so that's really what's stopping us from having big quantum computers right now. It's not the quality of the quantum hardware. I think we should be worried about that. So I want to say that quantum computers are a real threat. And it means that the cryptography that we're currently using on the internet is going to be broken. So we should start deploying post-quantum cryptography soon, and we should do that alongside the crypto that we're using right now. And why should we do this hybridization of using, say, ECDH and a post-quantum key exchange? Well, there's a few reasons. We first might have low confidence in the new schemes. Maybe somebody wakes up tomorrow and breaks all ideal lattice cryptography. But what we should really be concerned about is that we have low confidence in the implementations of these new schemes. We don't have much experience in doing it. So we don't really want to rely entirely on any of these new post-quantum things yet. We have good classical crypto, pre-quantum crypto. We should use it. Another concern, maybe not relevant for Tor, but some users do need things like FIPS 140 compliance. And so you have to keep using the things that are already in FIPS 140. So if we're thinking about quantum adversaries, we need to kind of think about 3 different types of security that we could have. We can have pre-quantum security. And this is entirely in the context of establishing secure channels. We could have pre-quantum security, meaning we have pre-quantum authentication and pre-quantum confidentiality. So that's fine as long as you don't think there will ever be a quantum computer, but I think there will be. So what you might want instead is something like transitional security, which is having pre-quantum authentication and post-quantum confidentiality. Now, authentication it's fine to have pre-quantum stuff as long as no one has a quantum computer at the time of session negotiation. If they get one afterwards, it would be a problem for the confidentiality. They could break the channel. But as long as they don't have one when you're negotiating your key exchange, it's fine. So that's an interesting use case to consider, adversary models to consider. And then you could go all the way to true post-quantum cryptography. You could use post-quantum authentication and confidentiality. But I want to focus on this case. And in particular, I want to focus on putting something into Tor to get transitional security. So that you get real forward secrecy. We say we have perfect forward secrecy. It's not really true. There's an expiration date on forward secrecy, and it's exactly when you get large quantum computers. Someone harvesting ciphertext at the entry node would be able to just bore through all the layers of encryption and break the anonymity and the secrecy of the channel. So we should be concerned about that. And so what we're going to do is put a post-quantum key exchange mechanism or key encapsulation mechanism into the NTOR handshake. Okay, so NTOR is a one-way authenticated key exchange. It was published in 2013. There's an engineering specification, Tor Proposal 216, and it's been deployed since 2013 as well. It looks kind of like this. So there's 3 phases. We can break it up into negotiating the pre-master secret, then doing this authentication tag, and then finally deriving a key. So in the first stage, getting that pre-master secret, that's 2 Diffie-Hellman handshakes. One of them is a static ephemeral, and the other one is ephemeral ephemeral. So our anonymous client generates a ephemeral Diffie-Hellman key, call that X. The lowercase letters are secret values, and the uppercase letters are public values. So they send their public value over to the router, in this case, the server, which has a long-term Diffie-Hellman key, which was denoted by A. And the server generates its own ephemeral Diffie-Hellman key, y, and it computes does two group operations. It does x to the little y and x to the little a. So the one using a provides authentication, and the one using y is going to be used for forward secrecy. They send y back, and the client is able to do the same group operations using their key. Okay, so that's the pre-master secret. Then we do some stuff with getting this authentication tag. This is for some more protocol level attacks. You want to bind the key that's derived to the entire transcript. You also want to make sure that you have a version identifier in there to prevent cross-version attacks and things like that. I won't talk too much about this just yet. And then the final step is you actually derive a key. Okay, so NTOR's great. It's got a proof of security in a totally fine model, but in order to talk about quantum adversaries, I want to consider a slightly stronger security model, one in particular that separates everything that happens before the clients accept and start using the key and everything that happens after that. So I want to be able to talk about a pre-quantum adversary during that pre-accept phase and a post-quantum adversary post-accept. So, sorry, that's the whole NTOR thing. So define a variant of NTOR that just makes it easier to give a proof in this particular model. The model is called the Authenticated and Confidential Channel Establishment Model. It's been used very successfully to prove the security of some cipher suites as they're deployed in the real world. So that was kind of the motivation for why to use it here. NTOR is already this thing that's out there. Why not use this thing that has a proven track record of being good in that scenario? So hybrid null is NTOR with a few modifications plus nothing. It's just NTOR with a few modifications. That's what the null means. And that's going to prove that that's a pre-quantum ACCE protocol. Or rather, the proof is in the paper, and you can go look at it if you want. So we have to make a few changes in order to get the proof to go through. The first is that we need to hash the static ephemeral share. It's just a slightly different assumption, hash Diffie-Hellman versus a gap Diffie-Hellman assumption. It's not terribly important, but I do think this is a good thing to do. It prevents some very theoretical attacks against very bad key derivation functions. The next thing is that NTOR, as it's deployed, does something a little funny with HMAC. So the first argument to HMAC here is supposed to be a key, and the second one is the message. And so NTOR is using a fixed HMAC key for all sessions, and that's fine as long as you treat HMAC as a random oracle. But I want to rely on the fact that HMAC is a pseudorandom function family. So I'm just going to take the public transcript stuff and shove it over into the key side of HMAC and use it that way instead. Again, this is just like a provable security thing. It's fine to assume that HMAC is a random oracle. There aren't any problems with NTOR, but I want to rely on the PRF property instead for the proof. And then the last thing is, well, really it's the same issue in the key derivation step. Just want to use HMAC as it's intended to be used as a pseudorandom function. Okay, so that gives us this protocol, hybrid null. It looks pretty much exactly the same as NTOR. It's a little bit simpler. There is one interesting thing, which we talk about in the paper, which is that we're using the same pseudorandom key for the auth tag and for the key. There's an attack if you choose the sizes of your symmetric functions very poorly. But as long as you're targeting, say, 128-bit security, as we are now, and using symmetric functions that are twice that size, you're fine. And against quantum adversaries, we need to do that anyway, because quantum adversaries get a square root speed up against brute force search. Okay. So going from hybrid null, this is the same protocol. I've just made room so I can add some new things. I want to talk about adding a key encapsulation mechanism to this, a post-quantum key encapsulation mechanism ideally, so that we get this transitional security property. So all we do, it's really the most obvious thing that you could do. Anyone in this room could have come up with it. You just do a post-quantum key encapsulation mechanism in parallel with the existing handshake. So the anonymous client generates a public-private key for some post-quantum key encapsulation mechanism. They send their public key over to the server. The server encrypts some random value to them and sends a ciphertext back. That's it. You do a few extra things in the authentication tag because you do want that to contain the entire transcript of the session. So that's hybrid chem. Talk about some performance stuff with hybrid chem. This is an instantiation with ntrue EES 443 EP1. It's 128-bit post-quantum public key encryption scheme, so it actually has the CCA2 property instead of the CPA property. Some people choose very different security estimates, want to be a lot more conservative in deploying things, so maybe this is kind of right at the 128-bit level. Maybe we want to be more conservative than this, but this is what we tried to start with. This is just a reference implementation of that parameter set, so the times here are pretty bad. But you can kind of see that it has a lot of extra communication cost, and the times for the client keygen is the only thing that's really substantially more than NTOR. The other two, excuse me, the other two protocols here, TAP is the legacy Tor handshake, so that was using finite field Diffie-Hellman. It ends up being comparable in time to hybrid with ntrue. And then this last protocol, Gauche-Kate, is another post-quantum proposal for Tor. It's specifically a ring LWE proposal. We wanted to make a modular thing so that people could try out different post-quantum chems, not pick winners at this stage, since we don't really know. It's still a very rapidly changing field. We don't know exactly what people will want to deploy, whether we want to optimize for size or efficiency or exactly what it's going to be. So, yeah, that's how we're doing on performance. Some other considerations. So right now, Tor only allows you to have 505 bytes in the create cell, and post-quantum keys and ciphertexts are generally pretty large. So looking across here, SIDH with that enormous prime number is the super singular isogeny Diffie-Hellman. This has been getting a lot of attention recently. It has pretty good sizes. It looks nice and small, but still that's over that 505 byte limit. ntrue EES 443, that's the one that we wrote our implementation with, 600 something bytes. You know, none of these things are going to fit. Fortunately, there's a new proposal that would allow for larger create cells. So hopefully in the near future, it would be possible to deploy some kind of post-quantum chem on production Tor. A few other things. It would be really nice to consider multi-cipher suite security. So is it okay to reuse this A component, the server's long-term secret, across multiple cipher suites? So say with NTOR or with hybrid null or with hybrid ntrue or whatever you're using. It's almost certainly fine to do. We just didn't complicate our security model to prove that. Another thing would be one-way anonymity. The NTOR paper defined a notion of one-way anonymity and proved that NTOR met that notion. They used some features of the authenticated key exchange model that to define that notion of one-way anonymity. Since we changed models, we can't use the same notion, but the other problem is that if you're introducing multiple cipher suites, that's obviously going to have an impact on anonymity. So really what we need is something that can do multi-cipher suite security and talk about one-way anonymity at the same time. If you have people using different key exchanges, they're reducing the anonymity sets. So that's a good area for future research. Another thing we could think about is actually deploying a totally post-quantum solution, so getting some kind of post-quantum authentication in there. Maybe using one of these new hash-based signature schemes in the directories to distribute long-term chem keys for the server. And then the last thing is that the type of symmetric crypto that's currently used uses, I think it's AES-128 in CTR mode. So what's currently used in Tor isn't good enough for our proof. We assume that you have some kind of authenticated encryption. So there are some proposals to upgrade the symmetric crypto that's being used in Tor. So something like that does need to be done before you actually get the guarantees from our proof. Okay, that's all. Thanks.